Introducing the Pareto Optimal Mapless Visual Navigator, POVNav, a novel vision-based perception planning control framework. POVNav comprises two main components: the navigability image, providing an efficient representation of the real-world environment, and the visual planner, which handles competing navigation objectives by identifying a Pareto optimal visual sub-goal and generating navigation features for visual servoing. Let's understand each component in detail. In the navigability image generation process, we categorize class labels into two groups: navigable classes like dirt, mulch, rock bed, asphalt, and gravel, and non-navigable classes such as grass, tree, vehicle, bush, sky, water, and rock. To create a binary segmented image, we assign a value of 0 to navigable space and 1 to non-navigable space. However, this simple classification sometimes leads to navigable regions being surrounded by non-navigable ones, making them unreachable from the robot's current position due to a lack of spatial context. To mitigate the issue caused by the simple division of class labels that disregards the correlation among classes, we introduced the concept of a visual horizon. The visual horizon update considers anything behind non-navigable segments as occluded and therefore non-navigable. It further assumes that any navigable surface surrounded by non-navigable segments is also non-navigable, as it is out of reach from the robot's current location. Though this process may omit certain navigable areas, it's not a concern during reactive planning. In the visual planning step, we transition from the 3D to 2D decision space, moving from the real world to the image representation. Here, we identify image pixels representing the robot's current state and goal. The robot's current state is determined by finding the closest point in the image to its current 3D state. The goal state is obtained by mapping the goal direction to the image boundary, known as the peripheral optic goal, POG. In the planning space, POG can be considered as the virtual goal whose direction aligns with the goal direction in the 3D world. Next, we define two objectives: F1 as the deviation of a navigation point, P, from the goal direction, and F2 as the distance traveled by the robot in the free space from its current position. Given these two objectives, our sub-goal selection task involves minimizing F1 and maximizing F2. These objectives may conflict with each other, and based on our observations, we found that for any non-horizon navigable point P, there exists a point P1 that dominates point P in terms of F2 while having the same value of F1. This is true for all non-horizon points. As a result, our search space is significantly reduced, and we only need to evaluate the horizon points to identify the optimal sub-goal, referred to as the horizon optic goal, HOG. In the given input image, where the goal is behind the tree, a Pareto optimal sub-goal is identified on the right side of the tree by evaluating the dominance of only visual horizon points. This figure shows the evaluation of the Pareto optimal set for visual horizon points, where the green points dominate the purple points. Finally, HOG is selected from the Pareto set by minimizing the weighted sum of both objectives. Finally, we utilize a modified A* algorithm to plan a path from the robot start state to the HOG, represented by the green line. This algorithm takes into account the safe boundary on both sides of the planned path, depicted by the blue lines, based on the robot's size. The visual path obtained helps us identify the features for controlling the robot. The linear velocity is controlled by the proximity feature, which corresponds to the closest point on the visual horizon from the robot's current state. This ensures that the robot maintains a safe distance from potential obstacles along the horizon. On the other hand, the angular velocity is controlled by the deviation of the planned path from the ideal path, which is when the robot is aligned with the goal direction, known as the alignment feature. Ideally, the deviation from the goal should be 0, and the horizon must be maintained at a safe distance away. This combination forms the error function for visual servoing, enabling precise control of the robot's navigation along the desired path. In summary, POVNav is a versatile and efficient visual navigation system designed for local collision-free navigation, utilizing only a monocular camera for perception, ensuring simplicity and easy deployment. The elegant design of POVNav enables real-time manipulation of the navigability vector, facilitating selective navigation behavior. By extracting the path from image features, it surpasses existing methods that evaluate motion primitives or shooting trajectories, leading to a substantial runtime improvement with minimal parameter tuning. Extensive validation through various simulations and field experiments further substantiates the efficacy of POVNav as a promising visual local planner. Thank you for watching.